Alright. For this one, this problem, we need to find the volume of the solid generated by revolving the region bounded by the graphs about the y equals 6. Right? So we are given two functions, y equals x squared and y equals 4x minus x squared. And I drew it over here. And I got the question from the paper and I just wrote it out myself. So here we're given this little model here, right? And the first thing I want to do is identify which one is the top function and which one is the bottom function, right? So with the functions y equals x squared, we know that that's a parabola, right? It's a regular parabola. And from looking at the function y equals 4x minus x minus x squared, so a negative x squared, we know that's just a backwards parabola. So it's right? So here, this little bottom function here, for me, resembles an x squared a parabola, just a normal parabola, upright parabola, right? So it's best to assume that this would be the bottom function, sorry. So I assume this would be the x squared. This function down here is x squared, and then the top function here would be 4x minus x squared. So 4x minus x squared would be for this one. All right. So now we have identified the functions. Which function is which? The 4x minus x squared is the top, x squared is the bottom. It's time to figure out whether or not we want to use a vertical or a horizontal strip. So a strip going this way, a strip going to the side. And one of the easiest and one of the fastest way to figure this out is just by looking at the functions given. We know if we're given y or x as a function, you know, f of x of y, we're going to be dealing with a delta x. And we know if x is a function of y, we're going to be dealing with dy. Right? So here, we're already given y equals x squared, the function of y. Y equals 4x minus x squared. It's already given to us. There's no need to do extra work and solve for x if y is already given to us. So we know we're going to be dealing with a dx, and we know we're going to be dealing with a vertical strip here, right? So this strip right here, and that's going to be delta x, right? That's going to be delta x. Already given to us. There's no need to do any extra work. Y is already given to us, so we know we're going to be using a vertical strip. We're not going to be using dx, delta x. So now we're told that it's being revolved around the y equals 6. Y equals 6 would be right here. And we're going to be revolving this whole entire area, the area bounded by these two functions. So these two functions, the top and the bottom function. So if we were to draw this out, just a quick little sketch, we would see what would resemble a washer of sorts, right? A washer. And to best visualize this in a 3D model, I'm actually going to pull this out, right? This is going to be a washer, right? And then pull out this best I can, draw it for it, right? Right, and then this right here is going to be the 6. So what's good to note about this, what's easy to see, is that there's going to be an open space in a washer. This open space here is going to have to be taken into account for, because we can find the total area of the outer washer. You can think of it as a disk inside of a disk. So this whole entire disk out here, minus the small disk in here, what's going to give you the area for this. Because this is open space caused by the rotation of the function. So we know we're going to be dealing with two separate radii. So we're given that it's rotating across around this y equals 6. The best way to look for the radius is by getting the total height, the top function minus the bottom. In this case, it's just going to be y equals 6 minus whatever function we want to deal with. So we want to identify this outer radius here. We want to find an outer radius as just r outer, right? We want to define, it's going to just be R outer, right? And then this will be radius inner. So we're going to be using this to find the area of what we can see as two discs inside of each other. So to find the area of the outer disc, we're going to be using the outer radius. So in order to find the area of a disc, is going to be pi r squared. But remember, we want to find the area. So in order to do that, in order to find the volume, we need to multiply it by a height. In this case, we're using delta x as a height. If you imagine it, it's going around like this. There's still a thickness of this pen. In this case, we can think of it as delta x, since it's going to be really, really small, times delta x. And that's the volume for the outer disc. And we still need to subtract it by the inner disc, because this is just blank space that the washer created. So in order to find the area, the volume of this, we need to subtract. We need to find the area of this. We need to use the radius. We need to use the radius of the inner thing. And in order to find that, volume pi r squared of the inner function. And in order to find these radii, we need to do 6, which is the height, the total height, minus the height of that function at whatever point. So the height at this bottom function here, the bottom bounds, is given by y equals x squared. We want to find the height at this point, so the top height minus the bottom height, and this height is given as x squared. X squared. So that's the radius for the outer function. So the radius for the outer function is going to be 6 minus x squared. Same process goes for the inner radius. Inner radius, the top height minus the bottom height. So with the top height still the same, 6. And the function, the height at this point of the function is given by 4x minus x squared. It's dealing with two different points. If you plug in 1 here, you'll be given a height. So that's the height at this point at x equals 1. In this case, it'll just be x. At height x, y is gonna equal 4x minus x squared. That's the height. So minus 4x minus x squared. Now we need to use these radii in order to find the total volume. So we got to plug them back in. I'm going to go plug them back into their volume. And remember, we're taking the volume of the outer disc minus that of the inner disc. So in order to really set this up, it would look a lot more like this. Pi r squared outer times delta x minus pi r squared inner radius delta x. Right? This would be the total volume, or the volume of this shape here. The shape, this one little delta x thick washer. Volume of this little element would be this. Now this could be simplified and cleaned up a little bit. So the volume of the element would equal, if you factor out a pi and a delta x, you would leave left with pi, right, r squared of the outer minus r squared of the inner function times delta x. No, this is exactly equivalent. The only thing is I just took it out. So this is just the volume of this one little washer that's delta x wide. We're going to be taking infinite amount of these between two different points, the intersections of the functions. So now that we figured out what the volume is of one little washer, we need to find the volume of an infinite amount of washers and sum them up using an integration. In this integration, we need to have a bounds, and this bounds is shown by the intersections of these two functions, right? So there's going to be bounds here and here of these functions of the area inside of these. So the integration is going to be from something to something of pi r squared of the outer minus r squared of the inner delta x, right? So in order to find the bounds, we actually need to equal the two functions, and algebraically work it out. Alright, so here I will do this on a separate sheet of paper. It seems we're going to be running out of room soon. The given functions that we have here are y equals x squared, right? Right there, and y equals 4x minus x squared. So we just equal them towards each other. X squared is equal to 4x minus x squared. Alright, so what we can do is add x squared and then subtract that 4x, put it on one side, and that's 2x squared minus 4x, now that equals to 0. Factor out a 2x, factor out 2x would be factored out here, so you're left with x minus 2 equals 0. And the only way to make this statement true is by having x equal either 2, so 2 minus 2 0, or 2 times 0 is going to 0 out, so x has to equal either 0 or x has to equal either 2. So this is going to be our bounds of integration here. 0 from 0 at this point 0, and this point 2, 0 to 2. Now as we worked out here, the radius is going to be 6 minus x squared for the outer, and the radius for the inner is going to be 6 minus 4x minus x squared. So we got to plug that back into our integration. And again, we're running out of room, so I'm going to rewrite it down here. This is going to give us the volume of the total area. So the volume of the solid region generated by rotating around the y equals 6. Alright, so volume total is going to be an integration from 0 to 2 of pi, and it's time to incorporate our r's here. So our r outer is going to be 6 minus x squared. That's our radius outer, and if we see here, it's squared, so we got to make sure we have that squared, that quantity squared, minus the inner radius here, so that'd be 6 minus 4x minus 4x minus x squared. All that has to be squared times, and instead of having a delta x like here, since we're going to be integrating, that's going to turn to delta x. It's going to be a delta x instead. As baby. And now it's just solving an integration. We have our integrand set up for the problem. Now it's just a series of algebraic steps to solve this. So we can start by taking out the pi to 0. And if you square this, would be squaring all this, simplifying this is going to leave you with x to the 4th minus 12x squared plus 36, alright, minus x to the 4th minus 8x to the 3rd plus 28x squared minus 48x plus 36, and then a dx down here, running out of room. So what we just did is distributed this over, simplified this. Now we're going to simplify it even further by distributing the negative and then adding them. So our volume total is going to be pi 2 to 0, and then adding this whole entire thing, assuming you can work that out, be 8x to the 3rd minus 40x squared plus 48x dx. Now, parentheses, now it's just integrating, which I'm going to do on a separate sheet of paper since I am running low on space. Just going to bring down what I had here. Pi to 0, 8x to the third minus 40x squared plus 48x, all that, right, dx. There you go. So integrating across, you need to bring down the pi. Well, 8x power 4, 8x 4 minus 40x to the third divided by 3 plus 48x squared divided by 2. Alright, all that from 2 to 0. Alright, now it's just a form of plugging in and then subtracting it. So pi 2x, or 8 2 to the 4 over 4 minus 40 to 3 plus 48 2 squared over 2 minus, if you plug in 0, subtract. You're going to subtract by plugging in the 0 here. Everything is just going to end up zeroing out. X to the 0 to the anything power, just multiplying anything by 0 is going to zero out the whole thing. So you're just going to be subtracting by 0. That's insignificant, so you can probably just cross that out. So really what you're left with is this. This is what you have to solve for. Just a simple addition that ends up simplifying to 32 minus 320 over 3 plus 96 pi. 96, right? You're going to leave the pi out and wait till the end. And once you add all this, 96, minus 320 over 3 plus 32, you'll end up with 64 over 3. And all that is times pi. Or just simply 64 over 3 pi. That's the volume total. That's the volume total generated by revolving the region bounded by the graphs about the y equals 6, given y equals x squared and y equals 4x minus x squared. All that.